on the darkest of nights, free from the glow of the moon and the haze of light pollution. A stunning, striking formation can be seen imprinted upon the sky. Ancient African observers knew it as the backbone of the night, while Polynesian sailors thought it to be the jaws of a cloud-consuming shark. And ancient Greeks even believed it to be a stream of milk, spilled from the breast of goddess Hera, which they called Gala, a prefix which would eventually give rise to the term galaxies. In the case of our galaxy, the Milky Way. Our galaxy is a giant which extends for hundreds of thousands of light years, yet its structure is more dynamic and evolving than we ever could have known. But thanks to the revelations of one particular mission, we're finally starting to unravel this great mystery by tracking the paths of stars to extrapolate our galaxy's past, revealing the history of the Milky Way. If you like what you see today, then please consider subscribing to help the channel. But otherwise, sit back and get ready, because it's a hell of a story. Our home galaxy. The Milky Way is an ancient, enormous barred spiral galaxy constituting a peanut-like bar of densely packed stars at the core, surrounded by a series of swirling filaments of younger, hotter stars and gas. This spiral structure makes up the thin disk component of our galaxy, which stretches for just over 100,000 light-years. But the true size of the Milky Way extends well beyond this visible component. Enveloping the thin spiral disk is a larger thick disk concentration of more eccentric stars, rising for thousands of light-years above and below the spirals. And even further beyond, we find the Milky Way's enormous galactic atmosphere, a diffuse halo bubble of stray stars, gas and plasma, along with the majority of its ancient clusters and satellite galaxies. In total, the Milky Way houses at least 100 billion stars, possibly as many as 500 billion, and about as many planets to go along with them. The Earth is one of those planets, lying 28,000 light-years from the galactic nucleus, taking around 230 million years to complete a full orbit. In contrast, stars further away from the heart of the galaxy can take up to 700 million years, while objects in the halo require in the order of 1 billion years to orbit. In reality, the Milky Way is far from the piece of synchronized celestial clockwork we perceive. The so-called spiral disk structure is more like a great galactic ocean, with each of its arms the consequence of a gravitational ripple, echoing a seismic event in the galaxy's past. And by measuring the common movements and speeds of the stars caught up in these ripples, we can reverse engineer them to reveal insights into the Milky Way's history. By charting the positions and recording the velocities of the stars in our galaxy, we can plot their paths through space. And both their past and future trajectories can be extrapolated. And the more stars we can probe for such properties, the greater the picture of the dynamic Milky Way we can build. And thus, the practice of astrometry remains at the forefront of our quest to map the Milky Way. Mapping the Milky Way. In the 1990s, our best effort in this endeavor was the European Space Agency's Hipparcos satellite, a star mapping probe which spent 3.5 years following bright stars to observe their movements through space. In 1997, its findings were assembled into the Hipparcos catalog, which listed some 118,000 stars with high precision, along with 1 million more at a lower rate of precision. And by the year 2000, improved data reduction techniques had broadened this number to 2.5 million, including 99% of the galaxy's brightest stars. Then in 2013, the ESA launched Hipparcos' revolutionary successor, the Gaia spacecraft, a much updated and improved star mapping probe, which measured groundbreaking high-precision properties for more than 1.2 billion stars. Gaia's first complete data release came on the 25th of April 2018. And in the months that followed, scientists used this earth-shatteringly vast and detailed dataset as the basis for supercomputer simulations recreating the Milky Way's development. And in doing so, they uncovered some astonishing revelations from its past. As we mentioned, beyond the thin, dense visible component of the Milky Way lies a giant, diffuse atmosphere of matter, the galactic halo. And it is this atmosphere that scientists believe was the first part of our galaxy to take shape. According to traditional models, in the earliest times before the epoch of galaxy formation, newly formed stars and gas would have concentrated within large, bubble-like gravitational wells of Matter. These attractors laid the groundwork for galaxies, like the foundations to a skyscraper. Then, over billions of years, the stars and gas contained within would have collected and flattened in orbit along a common plane around the heart of the halo, with the neat, cartwheel-like spiral structure in the gas emerging billions of years later. The bottom line is that the galactic halo was first part of the galaxy to form, and is thus where we would expect to find its oldest surviving stars. And indeed, we do see these ancient objects. Globular clusters. Bunched together into globular clusters, cities of early stars containing anywhere from 100,000 to a few million, all of which formed together, at the same time, from the same collapsing cloud. These clusters, some of which may be as old as the Milky Way itself, are believed to have gathered in the galactic halo in its earliest stages of formation, making them the perfect fossils, whose velocities and movements can be used to extrapolate backwards more than 12 billion years. And given their far superior size and brightness when compared with your average star, this enabled Gaia to map the movements of more than 150 distant clusters with excellent precision. And in 2020, this data was compiled and fed to the eMosaics neural network, which simulates a spiral galaxy's environment and evolution, this time incorporating the extrapolated paths of the ancient globular clusters by grouping them according to commonalities in their velocity. And in doing so, it revealed a far more dynamic and unstable history for the galaxy than we ever imagined. Even before Gaia, scientists suspected that the Milky Way may have had a violent youth. But we didn't realize just how violent it was. But the eMosaic simulations were able to attribute the lion's share of sculpting in our galaxy's structure to no less than 5 significant minor merger events, when the young Milky Way plowed into and devoured a progenitor galaxy, assimilating its stars and gas. And while 4 of these merger events were previously known to Kraken astronomers, there was one that took us completely by surprise, likely the oldest and earliest merger the Milky Way ever experienced, with a progenitor galaxy named Kraken. Kraken is thought to be the first large galaxy consumed by the Milky Way, colliding around 11 billion years ago, when the universe was less than 3 billion years old. Back then, our galaxy would have looked wildly different, far smaller, with less than a quarter of its present-day mass, and no spiral structure surrounding the core. At this time, a slightly older galaxy, Kraken, would have plowed straight into our own, bringing more than 100 million stars along with it, perhaps the most significant collision our galaxy ever experienced. While dwarfed in its size by the young Milky Way, this considerable merger event still bolstered our galaxy's collection of stars and gas by more than 10%, flooding the inner halo region with Kraken's stars and invigorating a huge new wave of star birth, kickstarting the formation of the galactic thin disk. But the puffier thick disk we see cloaking it today likely owes its bloated size to another galaxy merger event, which occurred later, and brought an even greater number of stars along with it, Gaia Enceladus. Gaia Enceladus. This galaxy, known more colloquially as the Gaia Sausage, or simply the Sausage Galaxy, was one of the first major revelations in the weeks following the 2018 Gaia data release. Within days, independent teams of researchers had teased out signs of a 30,000-member stellar aggregation, described as a blob of stars, rattling around the Milky Way's halo, with a departure of at least 210 kilometers per second from their local standard rest. By October, scientists had attributed this blob to our second significant minor merger, taking place a couple of billion years after Kraken. They named this galaxy Gaia Enceladus, and it likely played the principal role in forming the Milky Way's thick disk, supplementing it with more than 50 billion solar masses of stars, gas, and even dark matter, again boosting its mass by a tenth. This collision would have loaded the emerging galactic disk component with stars, sending swaths ping-ponging off for thousands of light-years above and below the thin disk. And this proliferation of more eccentric outlying stars today makes up our galaxy's thick disk. Most of the younger, high-metal stars we see floating around within the inner halo trace their origins back to Gaia Enceladus, either as imported stars or hybrid stars birthed in the Milky Way from extragalactic gas. Also imported were at least 8 globular clusters, some of which are the most well documented and studied of their kind. The Messier objects M2, M56, M75 and M79. And also the new General Catalog items NGC 1851, NGC 2298, NGC 5286. And finally NGC 2808, are all strong candidates to be the undigested, chewed-up scraps of Gaia Enceladus. But of this octuple, NGC 2808 stands out as the anomaly. NGC 2808, as it shows an unusual chemical composition when compared with other globular clusters. As we mentioned, the stars in these clusters usually form together from the same enormous, collapsing cloud which dissipated long ago. And so intuitively, all stars in a globular cluster should be the same age, with the same chemical recipe. But NGC 2808, on the other hand, does not follow this trend. Its massive stellar population appears to have emerged in phases, over a period of 200 million years. This suggests that it may not be a true globular cluster, and may instead be an imposter aggregation of stars that is similarly dense and ancient, but formed through a different mechanism. And the most likely explanation of such an object is the stripped, exposed core of the Gaia Enceladus galaxy, which was once home to its richest concentration of stars and stellar gas. Though the majority of the progenitor's structure disintegrated upon impact, the denser galactic core seems to have remained intact, and the aging, reddening stellar population resulting from its used-up gas now floats through space, reborn as a huge surrogate globular cluster. The only difference being the array of strange chemical signatures it shows. Omega Centauri, NGC 2808 may not be the only imposter cluster lurking within the halo of our galaxy. In fact, there is another, even larger cluster, NGC 5139, better known as Omega Centauri. This object is the biggest and most luminous cluster in the Milky Way, housing more than 10 million stars, unusually high for a globular cluster. And like the former, its stars have different chemical compositions, implying a staggered formation over hundreds of millions of years. This strongly suggests that Omega Centauri may also be the exposed, disrupted heart of another of the Milky Way's 5 ancient progenitors, known as the Sequoia. Like Gaia Enceladus, the Sequoia Galaxy. The Sequoia Galaxy was also discovered through the identification of a group of unique halo stars in the Gaia data which have retrograde orbits against the galactic tide, as well as a shared orbital eccentricity and chemical signature, all of which point to extragalactic origin. While probably less massive than the Sausage Galaxy, the Sequoia was likely older, and is thought to have joined the Milky Way at a similar time to Gaia Enceladus, around 9 billion years ago. In fact, it may be the case that these two progenitor galaxies were linked before their assimilation, sharing a relationship analogous to the present-day Magellanic Cloud galaxies. Like Gaia Enceladus, the Sequoia would have brought tens of billions of solar masses worth of new stars, along with 3 globular clusters among them. Omega Centauri, the multi-million member core of the former galaxy-turned-globular cluster. In addition, the cluster lies very close to an apparent tidal stream of stars, the Fimbultal stream, likely to have been torn from the outskirts of their host cluster as they were prized by the Milky Way's tidal gravitational influence. In fact, one of our nearest stars, Captain's star, just 13 light-years from Earth, is also thought to be a star lost from Omega Centauri, and thus the Sequoia Galaxy, which would provide us with a unique opportunity to probe an extragalactic object right here in our own backyard. The Helmy stream. Tidal streams like the Fimbultal stream provide us with a useful means to trace the path of a progenitor galaxy, and they helped sow suspicions that the Milky Way's structure was built up by accretion long before the revelations of Gaia. Back in 1999, physicist Amina Helmy, who also led the team who discovering Gaia Enceladus, examined data from the Hipparcos catalog, identifying a clump of 13 ancient, metal-deficient stars in the galactic halo, which shared a common angular momentum. In the decade that followed, independent analyses supported the conclusion that this is the product of stellar stream, named the Helmy stream, which was stripped from the fourth significant galaxy to crash into the Milky Way, around 7 to 8 billion years ago. And Gaia was able to shine new light on just How important this collision with the Helmy galaxy may have been in beefing up the Milky Way's halo. It identified more than 600 new members of the Helmy stream and recorded their velocities. And simulations utilizing this information showed that the progenitor galaxy may have contributed as much as 15% of the stellar mass in the Milky Way's halo, along with a whopping 15 globular clusters. In addition, among these many millions of stars, indirect evidence of an exoplanet around the constituent HIP 13044 was also detected. The hypothesized super-Jupiter-sized gas giant planet was proposed to account for a slight gravitational wobble exerted on its parent star. And if authentic, would make it the first planet of extragalactic origin ever to be identified. However, further analysis of HIP 13044's radial wobbles have failed to find more evidence supporting a planet lurking in the Helmy stream. But for the best and boldest of the Milky Way's Sagittarius dwarf galaxy streams, we need to look beyond the stars in our local slice. Rising high above the galactic poles, we find the Sagittarius stream, supplemented by the Sagittarius dwarf spheroidal galaxy, the fifth and final of the Milky Way's principal minor merger events. Sagittarius joined us around 7 billion years ago, and while small and insubstantial today, it has spent billions of years rising and falling into the Milky Way, puncturing its disk and spurring new star formation. Right now, the galaxy lies around 70,000 light-years from the Earth, and is on its way for at least its fourth in fall into our galaxy, the previous three coming a billion years ago, 2 billion years ago, and the earliest sometime between 5 and 6 billion years ago. With each iteration, it blew through the Milky Way's plane, decimating its own internal structure while sending gravitational reverberations cascading throughout our galaxy. Now, remember earlier how we likened the Milky Way's spiral structure to an ocean permeated by ripples? Well, the tidal gradients generated by these collisions are thought to be one of the leading causes of ripples in our galaxy's recent history, and thus may have been instrumental in carving out the spiral arm structure of our galaxy. At the very least, Sagittarius almost certainly sculpted the spiral arms both above and below the Orion spur containing the solar system, and would have ignited bouts of rapid star formation in our local neighborhood, the earliest of which came at a crucial time. 5 to 6 billion years ago, the Milky Way was starting to exhaust its gas reverses, following more than 7 billion years of breakneck star birth, causing star formation rates to plummet. However, the arrival and infall of Sagittarius rejuvenated our galaxy's metabolism. Perhaps only a billion years or so before the formation of the solar system. Perhaps Sagittarius is responsible for more than just the way our galaxy looks. Perhaps it also provided the catalyst that enabled it to harbor life. If nothing else, the Milky Way would look very different today without the many impacts of Sagittarius to ripple the Great Lake and flood it with new stars. Not least because, tracing the paths of these past encounters, we see the Sagittarius stream towering above the poles of our galaxy like the Wembley Arches. A feature that will persist long after the progenitor galaxy has dissipated into nothingness. Conclusion. With Kraken to kickstart its growth, Gaia Enceladus and Sequoia sculpting its disk, the Helmy stream feeding the halo, and Sagittarius to texture the spiral structure, the morphological mystery of the Milky Way can largely be explained. While we're still hunting for evidence of dozens of smaller and less significant minor mergers, we can be confident that these 5 ancient dwarf galaxies together account for most of the craftsmanship we see in the Milky Way. Our galaxy's morphology has constantly changed and evolved ever since its formation. Far from a flat, rotating disk, the Milky Way is more like a blizzard of stars, of which our solar system is but a single flake. And this snowstorm will continue to rage across space for tens of billions of years to come, absorbing the large and small Magellanic Clouds, before eventually crashing into the Andromeda Galaxy in its most significant merger event. And with new, contemporary star mapping efforts underway all the time, who knows what other incredible, inconceivable merger events we will find hidden in the history of the Milky Way?